Good morning, and thank you, Mattis. And thank you, Mattis, for coordinating and organizing a fantastic conference. Thank you. I'm going to be speaking today about the Bandit, the Housewife, the Samurai, and the Woodcutter, or since this is a DDD conference, I'm going to be talking about the importance of multiple perspectives in modeling. I'm Avraham Poupko. I work for a company called LNT, Larson & Turbo Technology Services. LNT recently opened a technology center in Jerusalem focused on security of software and hardware, and I'm the lead architect for that company. And I like to learn and teach and talk about how do people organize themselves to create software. It's a topic that fascinates me, and I'd like to share with you some of my thoughts on the matter today. 1950s, Akira Kurosawa directed a film called Rashomon. And in this film, a priest and a common man, he's called the commoner, are sitting and discussing a very disturbing and violent crime that had taken place a few days prior. And what's particularly disturbing about this very violent crime is that all the parties to the crime, mainly the victim, the aggressor, the innocent, and the not-so-innocent bystanders, are giving totally different accounts of what actually went on that day in the woods. Totally inconsistent with each other. To the point that the word or the phrase, the Rashomon effect, came to mean a complex event that took place, and different people are describing it differently. Maybe they're lying, but maybe they're telling the truth. They just see it differently. And by extension, Rashomon even means those events that can only be understood from multiple stories or from looking at them different ways. And in this particular movie, the stakes are high. They're very high. They're the highest stakes imaginable. Basically, the priest seeing the evil that humans are capable of and how they're not capable of telling the same story and taking accountability for what happened there, the priest is on the verge of losing his faith in humanity. And he says, this time I may finally lose my faith in the human soul. So now that we know what's at stake, we could talk a bit about complexity. Last year, the theme of the conference was Conway's Law. And we had Dr. Conway himself here in the audience, and I gave a talk. And in my talk that I gave last year, I showed this picture. And I said that when we design systems, we have three models that we are always occupied with. We have the model of the domain. That is the problem that we are trying to solve. We have the model of the system. That is the system that we are going to build that will address the needs of the domain. And we have the model of the organization. That is the way we organize ourselves in order to build a system that will address the needs of the domain. And I made the claim that the complexity of the system is always going to be greater or equal to the complexity of the domain. I said that there are no simple solutions for complex domains. Complex domains will have complex solutions, but you can have a complex solution for a simple problem. That's easy. We've all been there before. We know how to make a complex solution to a simple problem. I'd like to dive into this a little more and justify it and explain how maybe we could make this greater equals then a little closer to equals. So really, we could say that the complexity of the system equals the complexity of the domain plus something. Or more accurately, the complexity of the system equals the complexity of the domain multiplied by a number greater than 1. Now, I'm using mathematical notation here, but I'm just using the mathematical notation as a rhetorical device to make a qualitative argument, not a quantitative one. So the mathematicians among us, please be a bit forgiving. And I want to claim that when we talk about domain-driven design tackling complexity in the heart of software, complexity in the heart of software is this delta. How do we make systems that are no more complex than the domains that they are modeling or that they are addressing? We understand that the world is a complex place, and that if we're going to address the needs of complex domains, systems will be complex. We can't do anything about that, but we can try to make systems that are no more complex than the domain or no more complex than necessary. And of course, we have to address the question of what is meant by the domain. The domain means in this context, that part of the domain that we are modeling in order to find a solution for. So that is the domain. The domain doesn't mean the universe or the entire system that we are operating within. It means the part of the domain that we are modeling. So I'd like to talk today a bit about complexity, about models, about communication, and then at the very end, we'll try to tie it all together and make some sense of this, and hopefully not lose our faith in humanity on the way. So we've all seen this picture. David Snowden was here. I think are you in the audience, David? Professor Snowden? No. We saw the Cynefin model of complexity. And the most interesting part of the Cynefin model of complexity is the complex. That's why it's called the Cynefin model of complexity. And this is the quadrant where we have the most fun as software developers. We like solving new problems that have not been solved before. That's the domain where our skill and our ability and our intelligence is most often expressed. So we like the complex domain. We could call it the fun quadrant, as opposed to another quadrant which might be called the boring quadrant or the frustrating quadrant. And there are a few things about complexity that we need to realize. Complexity is temporal, I'll explain, it's emergent, and we have more than one type of complexity. Complexity is temporal. Complexity happens in time. A system that does not have a time element to it is not going to be complex. So a database schema might have very, very complicated relationships and dependencies. It will not be complex. In order for a system to be complex, it has to happen. Something has to interact with something. And when we describe complexity, we use words like feedback loops, experiment, probing, learning. These are all verbs with a very, very strong time dimension to them. And more so, it changes over time. Once it stops changing over time, it is no longer complex. So a clock does happen, a clock does something, a clock operates in time, but we might not say that a clock is complex. We might say that a clock is complicated. It has lots of moving parts. But in order to understand a clock, I don't have to experiment with it. In order to understand a clock, I just have to look at it and study it and see how it works. So the first thing we learned is that complexity is temporal. Second, complexity is emergent. I'm not talking yet about the solution. I'm talking about the complexity itself. Complexity emerges, and I'll explain what I mean when I use the term emergent. If something is, say, green, it's very reasonable to assume that all its parts are green. Green doesn't emerge from the togetherness. If something is metallic, it's very reasonable to assume that all its parts are metallic. If something is funny or beautiful, its parts might not be funny or beautiful. The funniness and the beauty emerge from their working together. And that goes for complexity. If something is complex, it doesn't mean that its parts are complex. I could have something very complex made out of simple parts, so I will say that complexity is emergent. For instance, let's look at the neuron. A neuron is not complex. A neuron is at most complicated, might be very complicated. We know how to model a neuron. We know how to predict its exact behavior. We know how to simulate a neuron. We know how to emulate a neuron. We understand neurons. We understand neurons really, really well. Neurons are not complex. However, take 100 billion neurons, put them in the brain of some moody, hormone-crazed teenager, and you'll get something really, really complex, borderline chaotic. And the complexity does not happen in any particular neuron, because the neurons are not complex. The complexity happens in the relationships between the neurons, in the interactions between the neurons. And it's due to this emergence that unit testing does not always deliver on its expectation, that unit testing does not always deliver on its promise. I could have a system comprised of units where each unit works exactly as expected, where each unit works exactly as specified, and no particular unit surprises me. And they all passed the unit test. And yet, the system acts in a surprising, unexpected, often failing way. And the reason is because the complexity of the system is not in any unit and can't be tested as part of the unit testing. The complexity of the system emerges from all the units together. So if we want to test the complex system, maybe we can't, but we want to test it at least to the extent that we can, we have to test it as a system. Unit testing will not test the complexity of the system at large. So we spoke about complexity, temporality, or in time, we spoke about emergence. And there is inherent versus accidental. These are terms that were introduced by Brooks in the 80s in a milestone article, in an important article called No Silver Bullet, Essence and Accident in Software Development. And these terms, inherent and accidental, mean different things to different people, and they're not really well defined. I'm going to try to give a working definition that will suit us at least for this talk. This is an ancient model of the universe, of the solar system. An ancient model, in ancient times, there was no real difference between the universe and the solar system. And the solar system used to be a very, very complex place. It was really complex. You were never able to, if you were an ancient astronomer, you were never able to predict when an eclipse would happen, when the phases, once we started seeing moons of other planets, when would the phases be? The only thing you could do as an ancient astronomer was observe an eclipse and then fit your model to explain why that eclipse happened when it did, or to give some other reason why it did. And the solar system was a complex place, but that was accidental complexity. Came along the geniuses, such as Kepler and Newton, and they didn't make the solar system less complex. They didn't have that kind of power, but they removed the accidental complexity, the complexity that people added on, and thus they made it more simple for us, and now the solar system is not even complicated. It's quite obvious or straightforward. On the other hand, if we look at, let's say, financial markets or weather systems, there's very strong reason to believe that there's no underlying pattern there waiting to be discovered that will one day make financial markets totally predictable. We believe that financial markets are inherently complex, and they always will be. How about computers? People often argue that computer systems are not complex, they're complicated, because compilers, languages, operating systems, interpreters are all deterministic. They all behave exactly the way they're specified. So maybe there's no complexity there. I think that's not true. I think that computers can still surprise us. And one of the reasons is, because behind every compiler, operating system, language, application, and platform, there are people. And there are people that wrote it. And they wrote it and tested it and implemented it and designed it and set requirements because that's how they think it should be used, and that's how it thinks it should behave. And once you have people in the picture, things are going to be complex. Now, when we look at the Cynefin model of complexity, Professor Snowden, did not reduce the inherent complexity of the world. Even he can't do that. But what he did do was reduce the accidental complexity of the world. And how did he do that? He said, if you recognize your quadrant and you behave according to your quadrant and apply the appropriate tools to your quadrant, you will have less complexity. And one type of complexity is misidentifying your quadrant. So, if I'm in a complicated world and what is needed is lots and lots of analysis, but I don't recognize that, and I think that I'm in a complex world, and I think that what is needed is experimentation, I just added complexity. What kind? Accidental complexity. Likewise, if I'm in the complex world, and what is needed is some experimentation, but I didn't realize that, and I think that I'm in the complicated world, and what I need is some analysis. Here too again, I increased complexity. What kind? Accidental complexity. And there's an interesting thing about complex systems. The more inherently complex a system is, the more we pay for accidental complexity. Complexity takes a price, exacts a price proportional to how complex the system is. Accidental complexity takes a price that's proportional to how inherently complex the system is. I'll give a good example. Let's say we have a toaster. Toasters are not very complex They might not even be complicated. And let's say I'm designing a toaster. And while I'm designing a toaster, I make a mistake. And I make a wrong assumption as to how people interact with their toast and with their toasters. And based on my mistake, I design the toaster differently. Chances are that toaster is still going to be a functional toaster. It's still going to be a useful toaster. It'll resemble any other kind of toasters we have. It probably won't end up having a volume button or an HDMI port or something like that, because it might become a one-pop toaster or a three-slice toaster, but that's about it. On the other hand, let's say I'm designing the emergency shutdown procedure for a multi-core nuclear reactor. Designing the emergency shutdown procedure for this nuclear reactor. And I make one small, wrong assumption as to how people behave during an emergency. Nothing really important. I think that people are able to follow, in an emergency, under stress, I think that they're able to follow a 3-item checklist, but in reality, they're only able to follow a 2-item checklist. Well, that's not such a bad mistake, right? We've made worse mistakes in our life. And that's a mistake that I make while designing the shutdown procedure for an emergency in a multi-core nuclear reactor. I could end up doing some real serious damage just by that one mistake. I add complexity that's going to take a toll in human suffering and in human life. So we say the more inherently complex a system is, the more we pay for accidental complexity. And one of the unfortunate things about accidental complexity is that we rarely realize it for what it is. We think that the accidental complexity is inherent. The ancient astronomers didn't say we are adding unneeded complexity to our model of the galaxy or our model of the solar system. They thought that the accidental complexity is really there. They thought that it's inherent complexity. Nobody that adds, or very few people that add an accidental complexity realize that that's what they're doing. The great British poet, William Wordsworth, and what makes poets into great poets, of course, is their ability to capture human truths in a very succinct manner. And what he says, William Wordsworth, is, he was probably talking about complex systems or something like that when he said, in weakness, we create distinctions, then deem that our puny boundaries are things which we perceive and not which we have made. We make the distinctions, and then we say they're part of the system. We didn't make anything up. We claim that they're there. Or as when the commoner and the priest are arguing about what happened there, so there's some great lines of dialogue there. The commoner says, well, men are only men, that's why they lie. They can't tell the truth, even to themselves. And the priest says, yes, that might be true. Because men are weak, they lie to deceive themselves. It's a sign of weakness. And then the commoner says, I don't mind the lie. If it's interesting, it's good. And the rumor has it, actually, that this commoner went ahead to develop a very successful career as a software architect. So he doesn't mind the lie, even if it's true. So we said that complexity is temporal. We said complexity is temporal, happens in time, emergent. It's not part of the system. And there's inherent versus accidental complexity. So now we have to ask the question, how do you model something like that? How do you model something that is temporal, where there's emergent and there's accident versus inherence? And the answer is, I don't know, but I have some ideas or some heuristics or some things to think about. So let's talk a bit about models. And when I talk about models, I don't mean the UML. I mean the set of abstract concepts that we use to model something. So let's talk about models. And the first thing we know about models is that models are wrong. All models are wrong. This is the model of the planet. It does not model every detail on the planet. If it did model every detail on the planet, it would be as big as the planet, and it wouldn't be useful, and it wouldn't be necessary because we already have a planet, and one is, at the moment, enough. So models have to be reduced. And as the bandit and the commoner are trying to talk about why they hide details, and the bandit says, these are not lies, these are stories. The bandit says, we all want to forget something, so we tell stories. It's easier that way. And as software developers, we know it. It's easier that way. So let's talk about the two types of models. They're descriptive models and prescriptive models. Descriptive models are models that describe what is. What is? A globe is a descriptive model. Maybe the world would be a better place if Amsterdam was next door to Manhattan. That might be, but any globe that has that is probably useless because the models are meant to describe the world that is, not the world that we wish could be or should be. And they're prescriptive models. This is the Phobos that's one day is going to take men to Mars or people to Mars and hopefully back. So this is what we call a prescriptive model. This is what it should be. And a descriptive model, domain-driven design, when we model the domain, we're not modeling the domain as it should be. We're modeling the domain as it is. And the better we understand the domain as it is, the more we have a chance of building a system that will address the needs of the domain and maybe even change the domain so the domain will one day become something else. But as a first-order approximation, we have to model the domain as is. And part of addressing complexity is getting your descriptive models right. And when we have models, there are a few stages. There's the model, there's the representation, the presentation, and we'll talk a bit about motivation. The model. The model is what Rosansky and Woods call the architecture. And this is something that happens in our minds as modelers. It doesn't happen on paper, it's not an artifact, it's an abstract model. We call this thing the model, the architecture, and truth is, not everything in the model is visualizable, can be put into paper. Models are sometimes very, very complex. Then we have the representation, what Rosansky and Woods call the architecture description. The architecture description might not carry everything that's in the model, and they might not be complete, even relative to the model, and they're written in a formal or informal language. Then we have the presentation. And by presentation, I do not mean PowerPoint. I do not mean PowerPoint. I actually like the words here of General James Mattis. General James Mattis is a general in the US Marines. He's a very strategic thinker and an articulate speaker. And he says that a PowerPoint makes us stupid. And so if you're wondering what it is, it's not television or Ritalin or social media. It's PowerPoint. Now, why does PowerPoint make us stupid? Well, it has to do with theory of knowledge. What does stupid mean, by the way? Stupid means there's ignorant and there's stupid. The ignorant hopefully knows that he's ignorant, and then he's going to go ask somebody or go to the library or attend a lecture, and then he'll stop being ignorant. The stupid person sometimes thinks he knows what he doesn't know. And if you look at the complexity model, the known knowns and the unknown knowns and so forth, there's a special place in complexity hell for those people that are confident that they know that which is not known and that which cannot be known at the time. Right? And maybe stupid appropriately describes us when we are in that mode, and all of us have been there at times. And the illusion, I could make a real strong argument that the illusion of knowledge is so much worse than ignorance. And PowerPoint sometimes provides that illusion. PowerPoint makes you think that something really complex can be reduced to a series of one-line bullets. I hope he wasn't talking about this particular PowerPoint, but he was talking about PowerPoint in general. And nothing complex can be reduced to some bullets, PowerPoint or otherwise. So we go to the presentation. I mean the actual telling of the architecture. A significant part of communicating architecture, have it in your head, put it on paper, and then present it. And you present it multiple ways. Imagine a story. The story happens in the head of the author. That's called the model. Then the story gets put on a book. That might be called the representation of the story. And then daddy or mommy tell the story. And they tell it again and again, and each time it's slightly different, even though they might be reading the same book. That is what we call the presentation, and that is when, hopefully, if we do it well, the model will come alive. And one of the things we could do when we present models is talk about the motivation. The models that we put on the two-dimensional space that we present very often don't carry rationality. They don't tell us why are they there. They don't tell us what objectives or goals. They just say object A has a relationship with object B of a certain type. But that's not where the real complexity lies, in the fact that there is a relationship. The complexity lies in why is there a relationship? Why is the domain the way it is? What objectives does the domain want to achieve? And even if you adopt thinking like Professor Snowden has said on occasion, that it is folly to attribute choice order and intent to systems, because systems don't make choices, only people make choices, that might be true. But there are people behind the domain that want the domain to operate in a particular way. Let's go through an example. This is an example that I took from a well-known book by Eric Evans on domain-driven design. And the example there is a shipping company. And in the shipping company, there is the cargo, and there is the itinerary that is going to hopefully satisfy a route that will take the cargo from where it is to where it needs to be. And if I look at this model, there's a line between the cargo and the itinerary with a little number here. And this line is sometimes called it's a relationship line, of course, and this particular relationship is called association. So I don't know what association means, so I opened the UML book, and the UML book tells me an association specifies a semantic relationship that can occur between typed instances. Now, this is not a very complex example, but for the sake of this talk, let's pretend it's complex. Let's pretend that there is some complexity in the relationship between the cargo and the itinerary. There's some feedback loop there, or there's something there of some complexity that happens. The fact that there is a semantic relationship that can occur between these two typed instances doesn't tell me anything about the complexity. Somebody has to tell me what the complexity is. How does a cargo, what does it mean satisfies a specification? How does a cargo choose from all the possible itineraries which itinerary is most appropriately suited? How do we build potential itineraries? How do we evaluate post factum if the itinerary actually did satisfy the route or not, and maybe it's time to go for a new itinerary? All those things are not captured here. So when I present the picture, I will tell you about it. And actually in the book on domain-driven design, besides this great picture, there's also lots and lots of narrative. That narrative is an attempt, a good attempt, to try to tell us these are the complexities of the system. Notice that the cargo works this way and the itinerary works that way, and so forth. And if I look at the movie and I watch about the relationship between the housewife and the samurai, the fact that there is a relationship is agreed upon all. That's not the interesting part, and that's not the scary part. What makes the story, the human story, so complex is what is this relationship? What is the nature of this relationship? How do people in that relationship act? What do they expect of each other? Now, an important thing about models, especially about representation, is that we always reduce a dimension. So here's a 3D object, and a 3D object has 4 representations. 1, 2, 3, 4. When I look at a 3D object from 4 points of view, I might be able to actually imagine the way it is. And the truth is this, I'll call it a projection. This projection is probably the best because it's one image taken from the exact right angle, so it allows me to actually imagine the thing in 3D space. But never forget, this is a 2D representation. If you really want to understand the object, you have to hold it in your hand and look at it from points, and maybe look at it over time. Now, when we model, the things in our head are dimensionless. The things that we put on 2-dimensional paper always have 2 dimensions. So we are losing a dimension. This is a projection. This is not the real visual graphical representation because things here in my head can't easily be represented. In particular, 2-dimensional artifacts do not well represent time. They do not represent time. Yeah, I put these arrows here, but these arrows are not really time. They're projections of time. They're conventions that help me imagine that there's time, but they don't really represent time. But we know that complexity happens in time. That's where complexity happens. And we know that complexity changes. Complex systems change over time. But this thing is fixed over time. It doesn't change. It's not changing. Here, I'm looking at it. No, doesn't change. See? So it doesn't change over time, and it can change over time. So how do I model something complex with loops, with time, and then I represent it in 2-dimensional space? I lose some of that. How do I get it back? By the presentation. I present the story. I tell you the story. And when I talk about a model, I can sometimes recapture certain complexities. I could describe non-visual things. I can describe things that happen in time. Now, in order for us to understand how that happens, how am I able to represent something in talking that I can't represent in modeling, we have to talk a bit about communication. That brings us to the part about communication. So we talked about complexity, and we said complexity happens in time, complexity is emergent, and there's some accidental complexity out there, lots. We spoke about models, and we said we have to differentiate between the model, the representation, and the presentation of a model. The presentation of a model is really important. There's the phrase, we all know, the phrase, a picture is worth 1,000 words. It's not true. A picture isn't worth any words. The only words a picture is worth is, or when is a picture worth 1,000 words? Once you've established a context, a social context, a cultural context, and then you look at the picture, then it might be worth some words. And how did that cultural context get established? How did that social context get established? More likely than not, with words. So a picture is worth 1,000 words only once context has been established, and that context has been established with words. So when we talk about communication, I want to talk a bit about language, spoken language versus written language. Two are different. And I'm going to talk about how we give meaning to words when we use language. So there's the spoken language and there's the written language. And one might think they're really the same, because anything that I could say, I could write. Anything that I could write, I could say. So aren't spoken language and written language really the same? And the answer is no. Written language is the language of science. It's the language of specification. It's the language of formalism. It's the language of patents. It's the language of mathematical proofs. All those take place and must take place in written language. On the other hand, spoken language is the language of drama, is the language of family, is the language of love, is the language of relationship, the language of friendship, the language of deep human communication happens always in spoken language, not in written language. And we, as a species, we have been speaking for eons before we've been reading and writing. And as individuals, we have been speaking and listening to spoken language and talking in some form of spoken language from our infancy, from our way, way tiny infancy. And we've only been reading and writing, some of us, those of us that live in cultures that have written language, we've been reading and writing from grade school, or maybe a little younger. And we know of cultures today that do not have reading and writing. And we know of cultures today that don't even have fire or clothes or some other things that we all assume are such an essential part of our lives. We don't know of any culture that doesn't use spoken language. Spoken language is deeply, deeply human. And some things must be said, they cannot be written. One of the people to write about this was a fellow by the name of Walter Ung. Walter Ung wrote about the transition from spoken language to printed language. The transition from spoken language to written language is actually covered by Plato in a series of very interesting debates and dialogues. And Walter Ung, who talks about orality and literacy, the transition from spoken word to printed word, says, print encourages a sense of closure. A sense that what is found in the text has been finalized, has reached a state of completion. That's the way print is. And that's certainly true for architectural artifacts that have been published and distributed. We think that they are final because they're printed and distributed. But complex systems are never final. They're never distributed. There's always something that's happening there that's because they happen in time. And once they stop happening in time, they're not complex anymore. Complex systems, when you print them, you're losing some of their complexity. But you could get that back when you communicate. So let's talk a bit about communication. Communication is about shared understanding, not about shared artifacts. You do not communicate by giving somebody a UML. That is not called communicating. And if I want to paraphrase a quip that's often made, I heard it from Jim Kuplin, we are paid to create understanding as architects. We are paid to create understanding. We are not paid to create artifacts. We might use the artifact as a platform for understanding. For instance, a context map. Wonderful idea, context map. Everybody should have a context map or two when they're doing projects. But unless the context map represents a shared agreement and a shared understanding and common use of the context map, it is totally useless. The context map on its own means absolutely nothing. The context map only provides value when people use it, when the people who have created and sympathize with it are able to use the context map. And one of the important things about using communication is the thing called theory of mind. And this we could do very, very well when we speak. We don't do it so well when we write. Theory of mind means when I'm talking to you, I'm imagining the way you see the world. And when you're listening to me, you imagine the way I'm seeing the world. And I'm able to imagine that. And recursively, we're able to come to some shared understanding. When I'm writing in a different context than the content is being read. So I'm trying to imagine what my audience thinks, but I don't get an immediate feedback loop. When I'm writing, I can't see that glaze of miscomprehension or that spark of understanding in the eyes of the audience, because the audience only exists sometime later, and it's hard to evolve a theory of mind when writing. So we give words meaning. Spoken words certainly have meaning. And when doing domain-driven design, we speak a lot about ubiquitous language. Ubiquitous language. And in order to use ubiquitous language, you have to use words, and words have to have meanings, and these meanings are not created by a dictionary. They're created also by a dictionary, but they're created by a dictionary and then by people using them, and by people using them in a particular way. When you want to learn a new language, so you might look up words in a dictionary, but really to learn a new language, you use the word. You see how it sounds to you see how it sounds to others, you see how it makes others respond, you see how people respond when you hear when they hear the word from you, and how you respond when you hear the word from them. And a word has three parts: the denotation, the connotation, and the association, and of course it all depends on the situation. Denotation is the way the word is defined in the dictionary. Pretty unambiguous. Connotation is those extra meanings or sentiments that we add on to the word. Association is other memories or things or ideas that the word brings to mind. And when we create a ubiquitous language, we use all of them together. And of course, everything has to be appropriate for a particular situation. So imagine the word accident. Accident denotation means an unplanned event or an unplanned unfortunate event that took place. The connotation of accident is sometimes something that should have been avoided, something that could have been avoided, something that I really wish was avoided. Yes, true, there's the fortunate accident, and there are other kinds of accidents, but accident, the connotation is very one of some judgment, some blame to go around. The association of accident is one of a car accident, a traffic accident, or maybe a child that had an accident, right? She didn't make it to the toilet on time, or he didn't make it to the toilet on time. These are certain associations that come to mind when you hear the word accident, and they might be used in a particular situation. So I'm walking down the hall at work one day, and I see you with a huge coffee stain on your tie. And I say to you, "Oh, I see you had an accident." And the connotation of the denotation of that is, I see you had an unfortunate, unplanned event. And that's what it means. And the connotation is somebody is probably at fault. Somebody wasn't as careful as they should have been. Maybe you, maybe the guy with the coffee. And maybe the association that comes to mind is that time that you as a teenager brought home your mother's smashed up BMW, and she looks at you and she says in that understated voice of hers, "Oh, I see you had an accident." And all that is captured in the word accident. And the word accident is a real powerful word, and that's the power of words. So if we look at our example again, we have the cargo and the itinerary. Cargo means things that go from here to there, right? Goods or merchandise conveyed by ship, boat, or plane from one place to another. That's cargo. The connotation of cargo is often something of business value. There's a business need for the product to get from here to there. Maybe it has to be priorities by time, by safety, by something. And if you don't get that about cargo, that there's business value in the shipping happening, then you don't understand the domain well enough, and I'll have to explain it to you some more. And the association that cargo brings to mind, well, maybe one of us might imagine a little envelope with 100 carats of diamond in it. Somebody else might imagine a tanker with 100,000 gallons of toxic nuclear waste, and somebody else might imagine another thing. And these are associations that the word cargo brings. And when we discuss the domain, and these matter, they're shipped differently, and they need different itineraries to satisfy their routes. You will not ship 100 carat of diamond the same way you ship a tanker full of 100,000 gallons of nuclear waste, I hope. And if you're going to build a domain model, and based on that domain model, you're going to be a system that addresses the needs of the domain, these things matter. So when you use ubiquitous language, it's not enough to use a ubiquitous denotation. You have to use a language that evolved. Okay? So we can try to wrap it all together. We said that the system is at least as complex as the domain that it is modeling. And we said that this delta is what we need to reduce. This delta is the accidental complexity. This delta is the delta that we add by increasing complexity onto the domain that might not be there. And we reduce it by creating a good model and communicating that good model and presenting that good model and presenting it in multiple ways. So we look at the story here. All the stories have in common that there's a relationship between the housewife, the bandit, the samurai, and the woodcutter. That does not differentiate one story or one narrative from another. What differentiates it is the type of the relationship. You speak to journalists or researchers or detectives or anthropologists, and they'll all tell you something very similar. They say, if you're investigating an event or a society or a culture, and everybody's telling you the same story, it's probably not a very interesting story, and you're probably not getting the crux of the complexity. Once people start telling you different stories, or different interpretations, or different narratives about a particular part of the complexity, a different part of the society, the culture, what it is, then you know, okay, this is where I want to dig further. This is where the interesting stuff happens. This is where I might gain insight. So if you look at a representation, it doesn't change over time. But if it's being presented to you, notice when is it being presented the same and when is it being presented differently. And when it's being presented differently, that might be interesting. That's where some complexities lie. Actually, detectives sometimes say something fascinating. Detectives say that the detectives learn more from the lies that people tell than from the truths that people tell. Now, why is it that a detective learns more from the lies that people tell than from the truths that people tell? Because when people tell the truth, they're all saying the same thing. And that might not be so interesting. Again, Rashomon effect not taken aside for a moment. But when people tell lies, each lie is different. And you listen to a bunch of lies, if you're a good detective or a good criminal investigator, you listen to a bunch of different lies, and slowly you get a picture of where the complexities are and what are people trying to hide. And this all happens in language. No detective will ever do an interrogation in written. He will always do the interrogation in spoken language. And one of the most complex human interaction is lying. Imagine the criminal and the detective in a battle of minds. And the criminal is lying because he has a theory of mind. What is the detective willing to believe about me? And what does the detective not believe about me? And then the detective is engaged in the lie, and he's thinking to himself, how stupid does the criminal think I am? What is the criminal actually trying to hide and what not? And this theory of mind, when you tell the truth, if you tell it in a naive way, you don't care what the other person thinks. When you're telling lies, lies are highly, highly complex, use a lot of theory of mind. And you describe all these things in spoken language. And spoken language allows you to go through levels of abstraction and levels of meaning really, really, really fast. I'm going to give you a few instances of dialogue, a few lines of dialogue, and I'll show you how I'm able to go in spoken language from class to object, from different types of ownership, in a very, very fast way. This is Eric Evans' book on domain-driven design. Everybody should read this book on domain-driven design if you want to know about domain-driven design. But you can't read this book, because this book is my book, and I'm not about to lend it to you, because I need it. It has my own dog ears, and it has my own footnotes. So if you want to read this book, go get yourself a copy of this book. Now, if I was writing that in written language, I would have to say things like this particular instance of the book, or things like the particular instance that the speaker is holding in his hand. It's not that easy when using written languages to go from a class to an individual, right? And how could this book be both Eric Evans' book and my book? You got that immediately out of context. Sometimes it's Eric Evans' book, and sometimes it's my book. It depends if I'm talking about the class of the book or the object of the particular book. And if we now look at our story again about the cargo and the itinerary. Same picture. I'm going to tell you a few different stories about this thing, which is not really complex, and maybe you will get the complexity of it. You'll understand it. I'll tell you some stories. So I'm a flower shipper. I'm a flower merchant. And I have a container with lots of flowers. And this container has to be shipped, and it has to arrive at the market by tomorrow morning. If it does not arrive at the market by tomorrow morning, it might as well not arrive at all. And I'm willing to pay a premium for that. If it does arrive by tomorrow morning's market open, then I don't care so much if it arrives an hour before the market, or 5 minutes before the market, or 2 or 3 hours before the market. As long as it's shipped and appropriately stored, those are my values. And if your shipping company could address my needs, I will ship with you. And us as a shipping company, we would like to address the needs. So that's the story of the flower merchant. The next guy is a geologist about to retire, a professor of geology on the verge of retirement, and he needs to ship his rock collection. home. And these rocks waited 60 million years. They could wait another couple of weeks. Nobody's in any rush for anything. And if they get lost, then our geologist will just take the insurance money and retire with it. He doesn't really need them. Or maybe he'll use the insurance money to get new rocks. There are lots of them where they came from. And he just really cares, get it there cheaply with as little hassle as possible, because I don't want to have to go to the post office to pick up my rock collection. It's heavy. And he'll tell you a different story about his needs from a shipping company. Then maybe we have the art collector. The art collector tells you, I need to ship my unique copy of Van Gogh, or Van Gogh as we say, from my art gallery to the exhibition. And I don't care about time, and I don't care that much about speed, but I care about reliability. If there is even a slight chance of this Van Gogh getting lost, then I won't have the exhibition, and I won't have the show, and the insurance won't help. No insurance money in the world could help me recover a lost Van Gogh. That's it. It's gone. So I have other needs from a shipping company. And they all are represented by cargo that has 0 or 1 itineraries that must satisfy a route specification. It must get it from here to there. But there's certain complexities, and again, this is not very complex. I'm using it just for illustrative purposes, that come along when I tell you the story of how I use the shipping company. And these are not use cases, and do not naively say, oh, so you mean that there's optimized for price, optimized for speed, and optimized for reliability. No, the flower guy is not optimized for price. Or for speed. He needs some speed and he needs some price, and the graph is really rather complicated. Maybe on the Monday morning market, he has one particular need, but on the Saturday afternoon market, he has another need. These are not things, if we can reduce some of the accidental complexity if we're able to create charts, but maybe we can't. Then comes along the other guy. He is a slave trader, and he needs to ship a bunch of slave children to work in some dark mine, and he needs a shipping company that'll help him avoid the long arm of the law. And hopefully, you have the moral backbone necessary in order to tell this despicable individual, I don't want to do business with you. Actually, I'm going to report you to the authorities myself. And suddenly, the cargo company has to start making moral and ethical and legal decisions. How much does he want to be involved in the morality and the legality and the ethicness of whatever it is that his cargo is? Does he really care about cargo? So maybe sometimes yes, sometimes no, sometimes a little. Sometimes it's in that gray area that if the reward is great enough, he'll be able to convince himself that it's okay. Sometimes it's deep inside the dark area that no matter what the reward is, he can't convince himself that that's a right or appropriate thing to do. This is really, really complicated. And these complicatednesses don't come through in this line called an association that is a semantic connection between two objects. It happens when we tell the story, and we tell the story many, many times. So if I was telling you the story of the 6 men of Indostan, in my story they probably wouldn't be blind, and I would say they're trying to observe the elephant, and they take turns. One guy goes and feels the tusk, the other guy goes and feels the tail, and they share impressions, and they say, well, what do you feel? And he says, well, I felt the tusk, and it felt a bit like a spear, and I felt the tail, and it felt a little like a snake. And then maybe they'll change positions and tell their stories again, and then maybe they'll observe the elephant over time, and then they're going to try to figure out what of these behaviors are specific to this elephant, and what are those behaviors true of all elephants. So maybe they'll watch the elephant interact with other elephants, and watch them over time, and then they'll watch other elephants over time. And then they'll invite an elephantologist or other people that are able to give them some domain expertise. And then they will slowly understand the elephant. And then they'll be able to use their models along with the gift of communication and shared observance in order to come at some insights about the elephant. So remember, our goal is creating a shared understanding, not creating a shared artifact. That's what we are to do. We are to create shared understanding, not shared artifacts. And understanding means, among other things, understanding the essential complexity. Not understanding what the domain does, but understanding the complexities underneath and behind and around the domain. And complexity always emerges from interactions. It's not in the parts. The cargo is not complex, itineraries are not complex, routes are not complex, flowers are not complex, rocks are not complex, geologists are not complex, but when they all come together, they can be very, very complex. And models and even the representation are just platforms for discussion. Part of what Eric Evans does in his book, in some cases when there are complicated ideas, he uses the technique of captured dialogue. A says to B, how do I model this thing? And B answers, and that's a technique in order to capture certain complexities. And what do we need? Well, I think what we need is, we always need new and better modeling tools, but maybe we need better communication tools, and maybe we need better communication techniques, and maybe we need to learn more about theory of mind and how people communicate complex ideas to one another and how people share knowledge, and we need to learn these things. So don't just read another book on UML notation, but try to learn from other disciplines, perhaps. How do people deeply and richly communicate? Read on about complexity theory. And of course, never lose faith in humanity and never lose faith in the human soul. Thank you very much. Thank you for your time and for your attention. Thank you.